This is the next example, verification example against the ISO standard thermal performance of windows, doors, and shutters. There are about 10 two-dimensional test cases presented in this standard, and we will consider only one of them. It is the aluminum clad wood frame section with the calibration insulation panel instead of the glass. Blue blocks are made of aluminum. Orange blocks are made of wood. This is the insulation panel, the calibration insulation panel. And this is the insulation, the resin. Temperature at the outside is 0 degrees Celsius and the temperature at the inside is 20 degrees Celsius. Our task is to calculate the heat flux and the two-dimensional thermal conductance. The two-dimensional thermal conductance is calculated from the total heat flux per length. This is the length, divided by the temperature difference between both adjacent environments. So in our case, this is the temperature difference is 20 degrees, and we should measure the flux. The main challenge here is to take into account convection and radiation heat exchange that present inside the air cavities. Some cavities you can see are closed and some cavities are slightly ventilated. The ISO standard recommends to adjust the thermal conductivity of the air so that the conductive flux will also include the radiation and the convection heat flux components. The procedure is described in details in the standard. It is essential that the convection flux is in direct proportion to the temperature difference and the radiation flux is in direct proportion to the fourth power of the temperature difference. So to find the effective thermal conductivity, we need to know the temperature difference. And to find the temperature difference, we need to simulate the problem. So this is the iterative task. First, we simulate the problem with some predefined value of the thermal conductivity of the air thermal conductivity. Then we find the temperature difference for each cavity. And we calculate the effective thermal conductivity for each cavity from the temperature difference. And then we run the simulation again and repeat the simulations until the process converges. I will create the new problem in QuickField. Specify the problem name and the location folder. The problem type is again steady state heat transfer. Here you should draw the geometry model, or you can import the geometry model from the DXF format. This is the geometry model. In the geometry model, you should assign label for each object. I hold the Ctrl button pressed to select multiple objects. This is the wood. This is the panel. Again, I hold the Ctrl button to unselect objects. This is the aluminum. And this is the rubber. And I have the air cavities. As I should calculate the effective thermal conductivity for each cavity, I specify different labels for each cavity. This is the air 1. This is the air 2. This is the air 3. This is the air 4. This is the air 5. This is the air 6. Those are non-ventilated cavities. And I have the slightly ventilated cavity. And I give it the label air ventilated. Now let's check. Air 1, air 2, air 3, 4, 5, 6, air ventilated, aluminum, panel, rubber, and wood. Next I should assign label to boundaries. The top boundary is the warm air contact surface. In fact, there is the different thermal resistance, the different convection coefficient at the horizontal and the vertical surfaces, so I should give this label air horizontal, and this is air vertical. And the same for the cold surface. This is air cold horizontal, and this is the air cold vertical. For the air, I specify the thermal conductivity of the air. As I do not know the temperature difference, I specify the thermal conductivity of the motionless air. And I repeat this for every air block. the aluminum, I specify the thermal conductivity of the aluminum 160. For the panel, I specify the thermal conductivity of the panel 0.035, and for the wood 0.13, and for the rubber 0.25. For the rubber 0.25, and for the wood 0.13. Next, I should assign physical properties to boundary condition. This is the convection surface, and I should specify the air temperature and the convection coefficient. The convection coefficient is a reciprocal value to this thermal resistance. So I type this value here. At the vertical surface, I have the same temperature, but the convection coefficient is slightly different. Now at the horizontal surface, I have the 0 Celsius degrees temperature, and the convection coefficient is the reciprocal value to 0.04. And for the vertical 0.04. Now I have the geometry model and the material properties ready. I can build the mesh, save all problem files, and run the simulation. Now I get the temperature distribution. I can adjust the field picture. I will switch off the color map and switch on the isotherms. To measure the heat flux, I should build the integration contour. I simply select the top surface, and this is the heat flux. Now, as I know the temperature distribution and I know the temperature difference, I can adjust the thermal conductivity of the air cavities. The procedure is described in the ISO standard. And we automated the task by using Microsoft Excel. So from our website, in the support, in the downloads free tools, you can find the equivalent air cavity thermal conductivity calculator, which includes the Microsoft Excel. Now I will show you how to use it. On this sheet you should specify the block labels, where you should calculate the thermal conductivity. In our case, these are these labels and air ventilated. So I type here air 1, 5, air 6, and air ventilated. Next, you should specify which cavity is isolated or slightly ventilated. Air 1 through 6 are insulated, and this cavity is slightly ventilated. Next, you should specify the initial value of the thermal conductivity, which is for the air is 0.035. Now, following the procedure described in the ISO and taking into account the convective heat transfer and the radiative heat transfer, the effective thermal conductivity coefficient is calculated for each cavity, and the results are presented here in the table. And this is the step 1 results, and this is the difference in percent between the initial and the calculated thermal conductivity. Now let's make the next step, and I will show you the QuickField. You see the QuickField is operated through from the Excel document. And again, for each cavity, the thermal conductivity is calculated. Now let's make 2 more steps. And 1 more step. You can see the ports are almost converged. The difference between 2 steps is less than percent. Now for this last result, let's find the heat flux. Again, I will switch off the color map so you can see better how the contour is built. This is the contour tool. I select the integration contour and calculate the heat flux. So this is the heat flux. Now let's calculate the thermal conductance as it is described in the ISO standard. I should divide the heat flux by the temperature difference. The heat flux is 5.38, 5.3798 divided by the 20. It's 0.269, and the reference value is 0.263. The difference should be less than 30%. Now let's calculate the difference. Divide by 0.263. The difference is indeed less than 30%. So we pass this test.